Hello class, this is chapter 1.6, and in this video we will be discussing exact differential equations. Now sometimes you will see a differential equation in this form, mxy plus nyx dy dx equals 0. Once in a while you will see this written in the form in this way: mxy dx plus nyx dy equals 0. So when you see it written like this, there's going to be an antiderivative that's assumed here, but it's almost never written down, so let's not do it now, okay? But that's what it means, even though it's not written down that way. That there's a secret integral sign on the left of all these terms. So a special class of differential equations of this form are known as the exact differential equations. And we say this differential equation, I don't know how to write Q, is exact when there exists a function f so that m is the derivative of f with respect to x and n is the derivative of f with respect to y. Okay? Yeah, I'm not sure why I wrote yx there and xy everywhere else. Let me just fix that. Alright. xy is everywhere. Okay, so if a function f exists that does this, then we say that this differential equation is exact. And exact differential equations tend to be easier to solve, and here's what's going on. So we can replace m with df dx, and what we have is, from here, okay, remember this implicitly antiderivative here. So this gets us basically implies that when we cancel the x's and the y's here, that we have fx y equals c. Well, actually it's going to be 2fxy equals c, but we can subsume the constant 2 into the c, which is just going to do that because c can be whatever we want. Alright? So whenever we have an exact differential equation, we can write down the solution as in this implicit form, fxy equals c. Implicit means that it's not a straightforward y equals solution form. It means the y is hidden inside some other expression, but that's fine. That's also a solution of some sort. So the question is, when can we determine if a differential equation is exact? And the answer to that basically comes to this. So remember that exactness means that there's an f where this equation holds, where mxy equals df dx and nxy equals df dy. So if that equation holds, then dm dy equals df dx dy, which is going to be equal to df dx dy, d squared f dx dy. But remember that we can switch the order of differentiation without any issues. dy dx, which is equal to df dy dx, but this is going to be equal to dn Okay, so in other words, we can determine that a differential equation is exact if and only if dm dy equals dn dx. Alright? Exactness of mxy dx plus nxy dy equals 0, if and only if we can cross terms that way, if the dm dy over dy equals dn over dx. And that's pretty easy to check, and once you have that exactness figured out, it's not that difficult to solve the differential equation, as we will see in the next video.